right, one more time. So, all right, last but definitely not least, electron scattering. Electron scattering occurs when photons are scattered, redirected by free electrons instead of being absorbed. Occurs when photons are scattered by free electrons rather than absorbed. It's also called Thomson scattering.
Oh.
Sound familiar?
Yeah.
Yeah. Where'd you hear about that? From the, I don't know, you've heard it from somewhere. I mean, Thomson's Mr. Electron.
Yeah.
So,
I remember reading something about it in my high school, in my senior
okay.
textbook.
Mm-hmm.
That's
Right, same guy.
Yep.
So, Thomson scattering is very nice in that the cross section for it is 8 pi over 3 times E squared over the mass of the electron times C squared. So the charge to mass ratio of the electron business.
Mm-hmm.
So E squared over MC squared squared. Put in the numbers, that's 6.65 times 10 to the minus 29th power square meters. It's a lot smaller than this, but that kind of makes sense because an electron is supposed to be a point particle. So that's not zero, but in other words, an electron doesn't look as big to photons as a whole atom does. It's not smeared out the way it is in an atom. And the nice thing is, notice there's no lambda here. So it's just this nice constant, independent of wavelength.
Wow.
And as we'll see, that means that it's what we call gray. In other words, the color gray is just in between black and white and it's colorless. So we'll talk about what's called a gray atmosphere, where we assume that the scattering is independent of wavelength. And so we say it's gray, colorless, so to speak. So this would be a form of scattering that's like gray, opacity that's gray. And gray can be spelled with an E or an A. But then the fact that it is so small compared to the bound free cross section, which is another form of continuous opacity. Continuous opacity means you can absorb at any wavelength, not just specific wavelengths. That's called line opacity. So bound absorption is line opacity, whereas bound free absorption and free absorption are continuum opacity. Any wavelength works. The fact that Thomson scattering cross-section is very small says that it only dominates when you don't have any of that. Or in other words, when the atoms are ionized so that you don't have bound free.
So like deeper in
the star, right? Deeper in the stars where that will dominate. Since the Thomson cross-section is much, much less than the bound free cross-section. Sigma t is much, much less than sigma bf. Thomson scattering becomes dominant only in very hot stars where everything is ionized. So in other words, there are stars whose atmospheres are hot enough for this, like O-type stars,
Yeah.
or deep in the interior of any star.
Is it possible for this process to occur in the accretion disk near a black hole?
I would think it would, yeah.
Because-
I would think so, because it's very, yeah, in fact, it would have to, because it's very hot, and so it's very ionized, so, yeah. Yeah, that's a good point, I never thought about that, but yeah, it would have to be an important source, yeah, of opacity and accretion disk like that. Thomson scattering dominates, only in the atmospheres of very hot stars. Where everything is ionized and deep in the interior of any star. Everything is fully ionized. So for example, the sun, you may recall from your project, the sun has the radiative zone underneath the convective zone. In the radiative zone, electron scattering dominates the opacity because everything's ionized down there. Now, turns out that photons can also scatter off the loosely bound outer electrons of atoms. Because they're hanging out, they're not attached very tightly, so it's almost like they're free, so to speak.
The photons would scatter off these electrons.
Yep.
These electrons are they required to be in a bound state, free state?
Yeah, because they're attached to the atom,
Okay.
and so they are in a bound state, and they stay there. But the photon can redirect. So in other words, essentially the photon just redirects without changing its energy. So you don't have to kick the electron out of the atom, but it's still interacting with the fact that it's a charged particle. Charged particles feel the effects of electromagnetic waves. And so, so in other words, it's too simple a picture to imagine that that an electron is just in an orbital in an atom, and a photon comes along and it suddenly jumps to a new orbital, all that kind of stuff. That's a simplification. Things can be more complicated than that. In fact, if you look at what's happening, it's not really something that happens in an instant. In other words, you can look at the electron's wave function as it starts to have a projection, a non-zero component from other orbitals. It starts out, say, in the ground state orbital, photon comes along and it starts developing projections, components along other orbitals. It becomes a combination of the ground state plus other orbitals. And if the photon has the right energy to cause a transition, there's a resonance where it can acquire a really significant component along, if you will, another orbital, a significant coefficient for including another orbital. And then you can view that as, okay, now if I measured the energy of the electron, there will be times when you'll have a significant chance of finding it at a different orbital. and that corresponds to then the transition occurs. If you see a photon, that indicates that a transition occurred. And it's also possible for a photon to interact with a bound orbital and change the shape of the orbital, if you will, because of the fact that it's a charged particle and there's electric and magnetic fields associated with the photon. And the result can be that the photon changes its direction while the electron never gets detached from the atom. It just changes its orbital shape for a while and then it goes back to the shape it was before, but it always stays attached to the atom.
So electron scattering from what I understood was that it's more of an interaction between the fields.
You can think of it that way, yeah. It's an interaction between the fact that you've got a charged particle and an electromagnetic wave, and the particle itself is generating electromagnetic radiation via this interaction, so that the net disturbance, when you include the original electromagnetic field from the photon and the electromagnetic field from the jiggling electron, is a new electromagnetic wave that corresponds to the photon moving in a different direction.
I see. Okay. Wow.
So they can scatter off loosely bound outer electrons of atoms, and that's called Compton scattering if the wavelength is much smaller than the size of the atom, and it's called Rayleigh scattering if the wavelength is much bigger than the size of the atom. So usually when we talk about Compton scattering, like in physics 280 kind of thing, you're talking about a free electron, but in a material, it's not really a free electron. And so typically you have it's scattering off of a loosely bound outer electron rather than truly a free electron somewhere. That's harder to achieve. So this is called Compton scattering. If the wavelength of the photon is much, much smaller than the size of the atom, and it's Rayleigh scattering in the other limit. And if you think about it, okay, so X-rays can have wavelengths that are smaller than the size of an atom. But visible light, do you remember what's about the typical size for an atom, roughly speaking?
About 1.5.
It's actually about a tenth of a nanometer, about
Yeah,
0.1 nanometer.
1.5 angstrom or something.
Yeah, something, right. It's on the order of angstroms, which is tenths of a nanometer. Visible light, however, is hundreds of nanometers, right? 400 to 700 nanometers. So for light passing through the atmosphere, is that going to be Compton scattering or Rayleigh scattering?
It's going to be for which?
For light passing through the Earth's atmosphere. Yep. Would it be Compton, wavelengths much smaller inside the atom, or Rayleigh, much bigger? It's Rayleigh scattering, okay? One can show with some quantum mechanical magic or a semi-classical calculation that gives essentially the right result, but really it's a quantum thing. The Rayleigh scattering cross-section goes like 1 over the wavelength to the 4th power. Yeah. So, in other words, short wavelengths are scattered a lot more than long wavelengths. In other words, this is why the sky is blue. The sky is blue.
Yeah, that's what I was about to say.
Yep.
This formula shows up in scattering when you're talking about.
Yes.
Is the proportionality the same when you derive it from quantum mechanics as well?
There's a correction, I think, or you put in some DS to make it. But yeah, it's essentially, I don't know, but it's either way you get 1 over lambda to the 4th, but I think you probably get a different coefficient to do it classically versus quantum mechanics. If I recall, I think you put in some BS into the classical contra calculation to make it agree with the quantum value. Here's this correction factor that makes it be the quantum value. I don't remember, I haven't looked at it for a while. But that's why the sky is blue. It's not reflecting the ocean, like parents tend to say. Well, they say that because they believe it, because their parents told them that.
Oh, jeez.
Yeah, and so on and so forth. That's one of those things that everybody knows, quote unquote, that's just plain wrong.
The myths.
It's one of those myths, that's right, yep. Another one is, people only use 10% of their brains.
Yeah.
And if they use the whole brain, why, they would be like superhuman or whatever. There's no way that evolution would create an organ that uses 20% of your oxygen and it only gets 10% utilization. That's ridiculous.
Yeah.
You use your whole brain. Anyway. For an H atom in the n equals 2 state, the ionization energy is, remember we use chi to indicate ionization energy, so that would be chi2. The ground state ionization energy was 13.6 electron volts. Here it's 13.6 over 2 squared, so that's 3.40 electron volts. So any photon with a wavelength less than the corresponding, less than what produces that energy, any photon with lambda is less than or equal to hc over chi2, right? Because the relation between energy and wavelength of photons is lambda is hc over the energy. So any wavelength with this, any photon with a wavelength shorter than hc over chi2. So hc, remember, is 1240 electron volt nanometers. And so chi2 is 3.40 eV. That's 365 nanometers. So in the near ultraviolet.
Yeah, that's pretty close to.
Yeah, 400 nanometers for. So that's in the near ultraviolet. Any wavelength shorter than that can ionize a hydrogen that's in n equals 2.
So anything above, like below 365.
Anything longer than that cannot.
Yeah.
Anything shorter than that can. Yes. And this has a consequence that the continuum opacity, in other words, opacity that works for every wavelength, the not spectral line opacity, has a sudden jump at 365 nanometers. It suddenly jumps up because now you can ionize the population of hydrogen atoms that are in n equals 2. So that's this extra source of opacity. Now these atoms that at wavelengths longer than that are transparent, so to speak. You're not going to be able to absorb those photons. Shorter than that wavelength you can. So there's a jump in what we call the continuous opacity. If you plot opacity versus wavelength, it jumps, and we call that the Balmer jump because of the fact that the Balmer series are the ones that start or end on n equals 2. So we call it the continuum opacity. Jumps below this wavelength. And that's called the Balmer jump.
When you said below this level, you mean any?
Shorter than that wavelength. Yeah. So in other words, if I were making, there's a figure in your book, and I don't have it up right now, but the idea would be here's lambda, and here is the opacity kappa lambda. Okay.
And the plot.
Then if you were making a plot, there's 365 nanometers, and this is not going to be a good sketch, but it'd be like, it would jump up because there's this new source of absorption above that. And actually, it tends to do something like that. The greatest absorption is just a little short of that. The absorption cross-section is highest when you're just at that wavelength, and then it starts to fall above that again. So the continuum opacity is where the plot is non-zero for every wavelength. And the last three opacities we talked about are continuum opacity, because any wavelength short enough to ionize an atom from a given state can ionize it from that state. Doesn't matter what its wavelength is, as long as it's short enough, shorter than the borderline, like 365 nanometers in this case. So bound-free absorption is a source of continuum opacity. It's zero longer than, for any given transition, it's zero longer than some wavelength, but then it's not zero shorter than that wavelength. Free absorption works for any wavelength, and electron scattering works for any wavelength. So those are all sources of continuum opacity. Bound absorption is line opacity, because remember that if you go from a bound state to a bound state, you need the specific wavelength needed to cause that transition. So if you were making a plot of kappa lambda versus wavelength corresponding to bound absorption, it looks more like this.
Oh, line opacity.
Yes, it's you know, how tall the spike is related to how strong, how probable that transition is to occur, how strongly likely it is that the electron will actually make the upwards jump when that photon comes along. And that differs for different transitions. They have different transition strengths. But the plot would be a bunch of spikes because it can only absorb its specific wavelengths. Turns out the spikes are not infinitely narrow. They're not delta functions, but they're very, very narrow. They're not delta functions because, remember, there's an energy time uncertainty principle. We don't actually precisely know the energies in an atom. But they're very, very narrow spikes. And then other sources of opacity are like this. So the total opacity is a superposition of some smoother looking curves with jumps in it, where every time a new source of absorption of ionization becomes available, the bound-free opacity jumps. And so you see these jumps, and then superimposed on that are spikes that correspond to line opacity. So the total opacity, if you plot it versus wavelength, it's horrible. It's just a mess because it's got all these lines in it, and then there's jumps, of just what happen to be the ionization energies of the atoms that the gas contains. And so it's just terrible. And so we're going to use what we call the Rosselin opacity instead, because it's just a lot of trouble to try to study the full opacity and solve the equations corresponding to that. So that's what we'll talk about next. So the total opacity will be the sum of the opacities due to each of these sources. So kappa lambda, the absorption coefficient at a given wavelength, will be the sum of the absorption coefficient for bound-bound transitions at that wavelength, plus the absorption coefficient for bound-free transitions at that wavelength, plus the absorption coefficient for free-free transitions at that wavelength, plus kappa for electron scattering, which again is not wavelength dependent. But these also depend, each of these is going to depend on the composition of the gas that the photons are traveling through. So it's an awful mess. And I'll point out again, this one is spiky. Non-zero only at specific narrow bands of wavelength. So in other words, this is the one that corresponds to spectral lines.
The line opacity.
Yeah, that's the line opacity. And these are all sources of continuum opacity. The line opacity is so complicated that if we're just trying to, if you're trying to make a really detailed model of the atmosphere at spectral line wavelengths, then you have to account for it. But if you're just trying to make an overall model of radiation transfer through the atmosphere, line opacity is so complicated that we just throw it out the window. That's what it comes down to. We just say, okay, what we're doing doesn't work at spectral line wavelengths, but it should work pretty well everywhere else. So, because kappa lambda has a very complex dependence on lambda, it cannot be used easily in atmospheric models. Cannot easily be used in atmospheric models. Like where we run computer code to model transport of radiation through the star's atmosphere. So we toss kappa lambda bound out the window. Be gone. And we use what's called the Rosslin mean opacity. Which we call kappa bar, that represents a type of average. Which is especially defined average, I'm just getting tired, average over wavelength. continuum opacities. So kappa bar is a function of what we call rho, t, x, y, and z.
Wow,
Yes.
that's a multi-variable thing.
Yeah, so the thing is, even this is a simplification because x represents the percentage of hydrogen, the fraction of hydrogen by mass in the atmosphere. Y is the percentage by mass of helium, and Z is the percentage by mass of everything else.
So
Metals. And we get away with that because metals are not very abundant. They make up at most about 4% by mass of the star's atmosphere. And the detailed composition, atom by atom, tends to be similar for different stars. So it's the overall fraction of metals varies more than the ratio of carbon to oxygen to nitrogen and so forth.
Yes.
So we can just get away with saying what's the overall fraction of metals in the star's atmosphere. So in other words, X is the hydrogen mass fraction Y is the helium mass fraction. So that's typically something like 75% is the hydrogen, and helium is typically something like 23%. And Z is the metals mass fraction. Typically something like 2%. And then rho is the mass density. T is the temperature. So in a computer program, one of the things you have to define is what this function is as a function of temperature, density, temperature, x, y, and z. Even there, it's not something that you write down. You have a table that people have computed for various combinations of rho, t, x, y, and z. And then you interpolate from that table locally in your program. You say, okay, my code says that it's computed at this location in the star, the density is this, the temperature is that, and the x, y, and z are these other things. Which typically, these won't vary unless you're in the core. And then you're just using electron scattering. So in the atmosphere, x, y, and z are just pretty much fixed for the star. But temperature and density vary within the atmosphere. And you'll have a table of a grid of values of kappa bar for various values of rho and t and your assumed x, y, z. And then you interpolate. You say, okay, well, my rho is in between these two values in the table, and my temperature is in between these two values in the table. So you use an interpolation formula to estimate what kappa bar is at that location in the star in your code. So it gets fairly complicated.
Yeah.
I mean, this is why people can make a career out of modeling stellar atmospheres.
Yeah. Someone doing this.
Yeah. I mean, there are these standard solar atmosphere codes that various people have developed over time, and they keep crafting them. And then there are model atmospheres for other stars that people have crafted very carefully over time. Our limb darkening coefficients that we use with the light curve inversion programs come from model atmosphere calculations. And so those are things that, it's something that you can be a specialist in, right? It can be your job to be, I model stellar atmospheres. So, yep.
Cause there's so much to do.
Yeah, because it's just crazy, yes. Because this calculation right here involves doing lots of detailed atomic physics calculations. And so then you create these tables, and then codes can use the results in those tables. So it's not even necessarily the same people. In other words, you might be making a model stellar atmosphere, and somebody else gave you the table of kappa bar as a function of rho and t, and you incorporate that table into your code. These kinds of things can be quite specialized, as you can imagine.
Wow.
And
High level of coding.
what's that?
That's an advanced level of coding.
Yeah, that's exactly right. Yeah, this is professional stuff. Is what it comes down to. Yes. So a real computer code will typically use detailed calculations of these, but there are some approximate formulae that have been developed that I'll write down here. You can have a bound-free Rosslyn amino opacity and a free Rosslyn amino opacity. And those are the two that you need to worry about, because again, bound we're just not even trying to do that here. There's no meaningful average over wavelength you can take for line opacity, because it's just too much of a mess. And it's a terrible approximation to try to average over wavelength when you've got a bunch of spikes. It's 0 at some places and big at other places. And the Thomson scattering is independent of wavelength, so that's not something you need to worry about averaging over wavelength. So these are the two contributions, number 2 and 3, where we need to make averages. And here it goes. So the bound-free mean opacity can be approximated by 4.34 times 10 to the 24th power GBF over little t of rho and temperature, z times 1 plus x, so the mass fractions here, z times 1 plus x times the density over t to the 3.5 power.
Wow.
And then the units are, because it's an opacity, meters squared per kilogram. Remember, the units are cross-section per kilogram. And the free mean opacity is 3.68 times 10 to the 23rd power G free GFF times 1 minus Z times 1 plus X